Okay, everybody, welcome back to our second video in this new playlist on equation drill down. In this video, we're going to talk about the state dynamics and the covariance extrapolation equations. So the state model, as we mentioned last time, looks like this. The state at time k is equal to the state at time k minus 1 after we've applied the state transition matrix phi and then added in some process noise, some uncertainty in the model. Now x itself is a state vector with n elements, so it's typically written as a column vector. And the process noise is also a column vector, so it looks like that. Now, some people prefer to make k a subscript and not have it outside like I have done it. But I choose not to do so because I want to avoid the clashes with the vector matrix elements that do use subscripts. So for discrete dynamics, we have to keep in mind that the Kalman filter doesn't work for nonlinear dynamics functions like we mentioned in the last video, but nonlinear models can be linearized, and we'll get into that further down the road, but just keep that in the back of your mind. So for the time being, we're restricted to matrices, and we're going to talk a little bit more about phi. Phi is called the state transition matrix. It's an n by n matrix because it's mapping a column vector of size n into a column vector of size n. And typically it's derived from a difference equation or a differential equation if those equations are constant coefficients. Then it will itself become a constant matrix that you can use over and over again. You just compute it once if the time increments delta t are also constant. It's often generated by an exponential matrix exponential, but we'll talk about that in the next video, or perhaps when we get more into the examples. So if delta t increments are constant, we don't really need to use the time index k. We can just use phi by itself. But we'll sometimes include the k just for generality. So the state dynamics matrix phi k is defined as that matrix which integrates the state, if you will, from the last time step to the current time step. It extrapolates the state vector, if you will, from time step k minus 1 to time step k, pulling from the past to the present. Now, as I mentioned, if delta t is constant, then for all t, we might as well just write phi of delta t, just to let us know. Or if we just set it equal to its first value, then just keep it as phi and not even mention delta t. But it is dependent on the difference in time between two time steps. So if you have a constant equal interval time steps, then that's fine. But if they're changing, then that's not going to work. You're going to have to go back to the full definition of phi. It tells us how the state would evolve in the absence of forcing functions. Okay, just keep in mind that this is still a model, right? And we don't really know what the true state is. And because there are random forcing functions that generate disturbances, we don't know perfectly what the state is. Okay? But in the absence of forcing functions, then we can pretend that there are no forcing functions, and we can integrate the differential equations or the difference equations, solve them, and come up with a matrix of phi. Other factors and terms often come into play in the full state dynamics model, and I'll mention some of them here. So we could have a matrix gamma that is applied to the process noise and spreads or distributes the noise variables across all the different states. And we could also have a control variable, u, which itself is a vector. It might not be at the same size. It might not be an n column vector. It could be shorter or longer, as long as then the associated distribution matrix is of the right size to make the result come out to be a column vector size n. So here's the full equation with all the bells and whistles. So we got our first part and our last part there with the WK, but with WK now possibly being shorter in size or longer in size, and then the noise being distributed by the gamma matrix. And we also have the deterministic control there in the middle, U, at time k minus 1, affecting the state at time k, and the distribution of control to the state variables is governed by the lambda matrix. Now, we're going to generally omit talking about the deterministic control variable because we're focusing on the estimation problem. Obviously, control is important in engineering systems, so we will have to consider occasionally, and it's important for you to learn how to factor that in. So the state estimate gets extrapolated via the phi matrix. So a question crops up right away. Why isn't the white noise sequence W included in this extrapolation? Well, the answer is because the white noise forcing function is a zero mean process. On average, that means this equation is homogeneous, and therefore we just need the homogeneous solution, i.e. the state transition matrix. Now the covariance matrix also has to be extrapolated, so we'll talk about that now. So, question, how certain are we that our solution is right? Well, the answer is given by a matrix that is formally called the estimation error covariance matrix. Often for brevity, it's just referred to as the covariance matrix. There are two other covariance matrices that are involved in Kalman filtering, and we'll talk about them in a minute. But because of its importance, the P matrix is often just called the covariance matrix. When people talk about the covariance matrix, they're talking about P. So like the state estimate, the covariance matrix has to be propagated forward in time before being corrected. So here's the forward propagation equation. You'll see that there's two terms, one involving phi and the other one involving Q. Now Q is a new matrix. It is called the process noise covariance matrix, and it measures the amount of dispersion or variance, if you will, or covariance, strictly speaking, in the white noise forcing function. So in a sense, it gives you an idea of how much the noise within the processes, within the states, are affecting each other. So later we'll learn how to define P, at least initially, also in terms of the expected error in the estimation. So you see this term down here, x tilde plus at time step k is equal to our estimate, our updated estimate at time step k, minus the true state. Now you can't really calculate this thing. This is just a formal definition because we don't ever really know what the true state is, right? But we do have our estimate, and we can define the P matrix as being a matrix formed from this error vector and its transpose. We'll talk about that some more later. But once we have it defined initially, then we just propagate P forward recursively and let the Kalman filter algorithm compute it at each time step. So we don't have to worry about its formal definition, really. Okay, so let's look at this equation. What does it really mean? What do each of these terms mean? Well, the first term, where we pre and post multiply P by the phi matrix and its transpose, in effect brings the state dynamics to bear on that error estimation covariance matrix. So because it's a positive definite matrix, and we're pre and post multiplying by phi and phi transpose, that automatically means it's kind of like multiplying by a square, and the values just get larger. So it grows. Its positive definiteness actually grows. Now Q, and that's what I just said there. So phi tends to cause the uncertainty to increase when you pre and post multiply like we've done here. Now Q is also a positive definite covariance matrix, so just adding it in is going to add more positivity to P. So as you can see, in aggregate, in extrapolating forward in time, the P matrix is going to grow in positive definiteness. Its diagonal elements are going to get larger. However, we'll see in the next video that we will be able to shrink those values by applying the measurement covariance, and that's what Kalman filtering is all about. So where are we now? We've drilled down on the state dynamics. We've introduced the P, the phi, and the Q matrices and discussed the time extrapolation of P. What's next? We're going to drill down on the Kalman gain equation as a function of P, Q, and R. And then we're going to present the 5 fundamental Kalman equations for the general solution. And that'll do it for today. We'll see you in the next video.